So thanks for the introduction. I'm Bryan, and this is Nitish. We're going to kind of split the talk, so at some point we'll make a handoff. But we're talking about the decathlon, and we'll go into some details, but I want to encourage everybody to ask questions along the way. If there's a word I throw out that you're not sure of, don't worry about it. We've timed it in such a way that you can interrupt us, and I'd rather explain things than lose you early on or anything like that. So let's just jump right in. Since we're from Salesforce Research, I wanted to talk a little bit about this guy. I ruined the effect of the animation, but Einstein is basically the organization, or a sub-organization within Salesforce that harbors all of the AI everything. It's essentially all of Salesforce Research. It's all of our product teams that are related to AI, all of our engineering teams, and all of these teams work together to give you things like Einstein Voice or any of our other AI applications like intent, classification, things like that. And one thing that, if we have some time afterwards and you want to talk to us about, we're really excited about this new shift in our group towards AI for social good and ethics in AI. We have new positions specifically for that, and we're really trying to be conscientious about how we use AI in the future. So if that's something you're interested in, also come and chat about that. But today we're just Salesforce Research here, and we have a lot of different kinds of projects we work on. This one's an NLP project, but I want to make sure everybody knows that we're not just an NLP lab. We're not even just a computer vision lab. Really, we work on anything from reinforcement learning to applied applications, like I mentioned, like Einstein Voice. We work on kind of education around AI through Trailhead. Salesforce has this thing called Trailhead where we design classes and try to kind of introduce things like deep learning or deep learning for NLP. But this time it's just going to be research. But all of these things you can email me or Nitish and ask us about in the future. Before we go into the project, I should also mention that Siming is our director of research and Richard is our chief scientist, and they were they're awesome, and if you ever get a chance to talk to them, they're just super brilliant, and it was amazing for us to work with them on this project as well. It's kind of a dream of all of ours to kind of work on this direction more, so it's been a good time. And we came to this project asking what we think is next for NLP. Not necessarily even last year when we put this work out or next year, but in the long term, where do we think it's going? Kind of taking a step back and looking at the trends, what do we think are some fundamental problems that might last for a few years and are things that we really need to figure out if we want to understand natural language understanding more. And the thing that we first noticed was that most of NLP revolves around single task learning. So this usually involves a group, a team, maybe just an individual scientist or someone, designing a model for a specific data set, a specific task with a metric that they can optimize and just focus on that. And as a community, we are really good at this now. I think we have the tools to kind of approach most problems that we're working on. And at least in the research community, if you release a data set now, sometimes it's solved before it gets published, right? So people are quite good at this. But this also has some limits in the long run. Basically, every time we get a new task, or you want to optimize a new metric, or you get an entirely different data set, or anything like that, usually we go through this iteration cycle of designing a new model. And this can be really helpful. I mean, it is, right? This is how the community has worked, and we learn something new from every task, and we usually kind of carry insights forward. But every time we want to approach a new task, we end up kind of training from scratch or almost from scratch if you're using things like pre-trained word vectors, and the cycle repeats. So this is the main trend that we were looking at, and we wanted to see how we might move past this trend. One way to do this is to try to do something called transfer learning. If you're not familiar with that, this is just saying we have some task, first task, task A, and what we do is we take a model and we train on task A, and we're hoping that while the model is learning how to do task A, it's also just learning general features that are useful for natural language other tasks that we'll call downstream tasks. So once we have Model A and it's trained and it knows how to do something like question answering, maybe we can then use it to kind of teach Model B, or maybe we can fine-tune it for other tasks. Anytime we're doing this, we're transferring knowledge from one task, one model to another, and this is what I'm referring to as transfer learning. One thing that is really promising about transfer learning is that we've seen a lot of success with it in computer vision. So if you've heard of something called like ImageNet or convolutional neural networks, then the community is really good now, like training these giant conv nets on ImageNet really fast, on a lot of different devices. And we found that a long time ago that if you train on this task, like ImageNet, image classification, then the neural network learns features that you can transfer over to other computer vision tasks. So then you can do things like caption images without training the image part of the model and just train the language part using features from the image part. So that's a sense in which we're like transferring knowledge from the image domain over to this image captioning domain. And for computer vision, things weren't so great before ImageNet and before we mastered classification, and then once we did that, it kind of took off. So classification was kind of the blocking task for computer vision. But in NLP, things have taken, we say much longer. I guess it's like a few years, like 4 or 5 years or something like that, where we've had word vectors for a long time. Things like word to vec or glove, if you're familiar with those algorithms. We've had things like sentence vectors and paragraph vectors that try to build on that. We had some work in 2017 on contextualized word vectors that transferred knowledge from machine translation to question answering and text classification. And last year, there was a lot of work coming out on like language models that were pre-trained to just kind of generate the next word in the sequence and then transfer that kind of general language prediction model to the same kind of tasks, like question answering or classification. So we're starting to see it take off, and it's actually really exciting, except that transfer learning also has some of the drawbacks that single task learning had. Essentially, every time you get a new data set and a new metric, you often have to have a new model that goes with your pre-trained portion of your model. So if you have model A, you usually need a model B. Even if it's a small model B, you usually need to add it. And then you're training less from scratch now, but you usually have to train a little bit as well. And then we still repeat this cycle. So what we wanted to look at was, well, let's think about all the tasks in NLP we can, and all the tasks we can kind of hold in our head at once, and think about which ones might form a basis set of tasks that really would help a model understand many different features of language, and also require us to design a model that is not particular to any task, but really can do maybe all of the tasks that we would want it to work on. And multitask learning, there's a lot of research on this going back many years, and it's always been really hard because you have a lot of different data sets at that point, and you're trying to train them all at the same time. It's not like in transfer learning where you can usually train on the first task and then kind of forget about it and just use what you know. And as you're training model B in transfer learning, you can kind of forget about task A and model A, so it doesn't matter. But in this case, we want to do well on all the tasks at the same time. And we also want to hope that this gets at something allowing the model to generalize to new tasks that are kind of covered by the basis of a task we provided. And going back to the computer vision NLP comparison, it was actually really interesting to see how in computer vision you don't see a whole lot of multitask learning beyond different kinds of classification or things like that. If you have very different tasks like object detection or segmentation and things like classification, a lot of these have really different output modules, or like the outputs look different. So it's a label for an image, or bounding boxes for where something is, or you're counting the number of things in an image. And those are kind of in different answer spaces. Whereas with NLP, and the tasks that we consider, most of our answers actually do or can be phrased as some form of sequence of words, which makes it a lot easier in some sense to design a model that is general enough to handle a lot of different kinds of tasks. So things like machine translation, where we're going from one language to another, or semantic parsing, where you might take natural language and then convert it to some structured query like SQL, or things like question answering. All of these, usually the output is some sort of sequence of words. So our hope was maybe we can actually go further with multitask learning and NLP because of this natural unification of the answer space. And you might ask why we want to do this. Well, one of the reasons is that it's an interesting intellectual question, right? Like, we use language in a very flexible way. We use it to do a lot of different kinds of things. So in some sense, you could argue that we're a kind of natural language system that has this unified approach to language and uses it to interface with lots of different things. And this is just something that models in the NLP community don't really have right now. And especially like the people that worked on this project really saw the multitask part of this project as a blocker if we want to understand where to go towards more general kind of NLP systems. There's also some kind of practical motivations that we've mined from the past as well. With deep learning, we kind of moved from handcrafted features where we said, this is the important thing to look at, model, and then we moved over towards, hey model, just look at this and decide what's important, and you do your thing. We're hoping that we see something similar like that with multitask learning, even like transfer learning too, where maybe a multitask model can look at all these tasks and decide which knowledge to share, rather than me saying, hey, task A is important for task B, task B is important for task D, but task D is not important for task C, which is, again, getting in that really like handcrafted space. And we're trusting kind of the magic of deep learning to help us out here and maybe figure out these relationships and figure out how to make them work when it might be too complicated of a problem for us to like hold in our heads once we move to lots of different kinds of tasks or very different kinds of tasks. And on top of that, if we did have a unified multitask model, we're hoping that eventually we can teach it to adapt to new tasks because it will have some sense of like what language is, and it's seen a lot of different things. Just like on deployment and production, if you can deploy a model that can do 10 different things, that saves like our engineering team a lot of time. And we're also hoping that, like, because we've open sourced the code and everything, that it's kind of easier to conceptualize all of these tasks together, and in that sense lowers the bar for people to enter into NLP and think about these problems, like clear it out with the model, and like just get more minds focusing on these things. So then we asked ourselves, okay, we believe that multitask learning is important. We think it's this problem that we should solve if we really care about understanding natural language processing. So let's look at all the different kinds of tasks that happen that we do in NLP. Let's take at least some of them, that's a diverse set, and try to design a model to work with those. So in this list, you'll see a lot of different things where the models for these tasks are usually quite different. Like with a question answering system, the predominant approach still is to kind of do span extraction, where you look inside some document and you kind of copy the important words. Machine translation, you have to generate words in another language. Like a question answering model never has to think about that, right? So usually they don't even consider that. And the model like is not capable, like mechanically in some sense, of doing translation. Things like summarization, natural language inference, these are all very different. And we'll kind of get into some of the details, and as these tasks become important to talk about, we'll kind of dig into what they are. But for now, it's okay if you don't like know exactly what all these tasks are. But what we wanted to do was unify them in some sense so that we could even start thinking about them as a single thing. And we came up with essentially three, what we think is mostly equivalent paradigms for approaching all of these tasks together. The first one was language modeling. So language modeling is essentially just looking at a sequence of words. It could be like a stream of text going back into infinity or forward into infinity. And your goal is just to predict the next word. You see some number of words in the past, and you predict the next word. And in some sense, if you could do that, always, then if I gave you an English sentence and asked you to translate into French, and I said, just translate into French, and you're supposed to predict the next word after the English sentence and after my question, the right answer would be the French sentence. In some sense, if you had a document and you asked something about the document and you said, now what's the answer? The language model, if it was going to predict the right word, would have to give you the answer. So in that sense, it's okay if that's a little fuzzy. We can talk about it later. But language modeling for us represents kind of one of these general approaches. Question answering is also one of these approaches, where you can take any NLP task, or most, and frame it as having some sort of context that you give to the model, and then you ask the model some sort of question. So for machine translation, you might give it a sentence and say, what is this sentence in French? For semantic parsing, you might say, this person said this in English, what is the SQL query relating to this database? So all of these things can be formed as question answering. And then there's also dialogue, which we kind of see as an iterative form of question answering that might have maybe some memory attached to the model or something like that. But we chose to go with the middle one for this project. We wanted to focus on question answering, primarily because if we want to venture into language modeling, we're hoping that maybe we could do everything as question answering and then just ask the language model to predict the next word. So these things are compatible. If you want to do dialogue, you could just keep asking different questions, and then now you have a dialogue. So question answering seemed like it was really this nice middle ground where we had models we already understood really well, and we wanted to work off of this and then maybe extend it in future work to some of these other kinds of tasks. So we're just working in the context of question answering, and I want to give some sense of what that really means. So we had these 10 tasks from before. All it means to treat multitask learning as question answering is to say, let's design a single model where all of these tasks are going to have a context, a question, and an answer. They're all sequences of tokens, so it's just sequences of words. And we're going to assume that the context is more or less enough information to answer the question. So we're not dealing with world knowledge that isn't accessible or anything like that. That's, again, some cool future work that we hope to get to. But these are some concrete examples. So the first one's easy. This is in the same order as on the previous slide. So the first one just is from a question answering data set, where the questions, it's like, what is the major importance of Southern California in relation to California and the US? There's some context, which in that case is a Wikipedia document, and then the answer is major economic center. Maybe for like a very different one, if you look kind of in the bottom right here, or like down here for people that are like looking online, we're basically giving a context which contains all the column names and the table name for some sort of database. And then we say that the human said, tell me what the notes are for South Australia. And we ask, what is the proper SQL query that we should use here? And then our model actually generates a SQL query based on that information. So those are pretty different things, but they're still question answering for us. And these things work for, like who had given help, Susan or Joan, or for the context, like Joan made sure to thank Susan for all the help she had given. This is the pronoun resolution, which is actually probably the hardest task, because this kind of identification that like she is related to Joan or Susan is just very hard for these kinds of models. And again, like this is something that we can come back to if it's important, just asking about any particular task. Yeah?
Is this what you mentioned is open source?
Yeah, all of this is open source. So for example, with the open source code, you just like hit a button, you say go, and then it downloads all of these data sets. All of these are public. We didn't want to use any private ones for this reason. And then it pre-processes it for you, and it'll just like run the model. One thing I'll mention too is that a lot of these tasks are different in the sense that the red words in the answer are highlighted in that way because they are in the context. So that's where the source of information for answering the question is. Or the green ones, those answers are somehow in the question. So for classification problems, we always ask, like, is this positive or negative? So that's how we're kind of telling it to focus on that task. The blue ones, the blue words, just have to be generated. That's something like machine translation where you don't actually look at the context for that. Yeah?
So the code is not.
Everything for this project is open source. Every line of everything I've ever written. Except for the things that I didn't want.
Can you train this on one data set and then apply it on another data set, like you do transfer learning after you train?
Yeah, that's a great question. And Nitish will talk a lot more about the experiments. But there's a lot of different settings that we tried, and we explore kind of how these data sets relate to each other. So for example, if you train on the question answering data set, you'll end up actually doing pretty well on the zero-shot relation extraction data set or on the question answering semantic role labeling data set. So there's definitely some relation there, and you can capitalize on those if you don't care about all of them. Yeah?
Is the context actually that raw human readable text that you're feeding in, or is it actually structured in some way and then you're just presenting a summary of that structure?
So I guess it's as raw as it can be.
Okay.
I mean, it's converted to numbers and then word vectors and things like that.
Yeah.
But that is what we give it.
Okay.
These are real examples. Is what I should say.
So
And the
it's
answers
inferring from the
are also sequences of words. So it doesn't, when it's doing sentiment classification, it's not a two-class classification problem. It has to generate the word positive from the set of all the other 800,000 words it could generate. So it actually has to understand in some sense what positive means to do that sentiment classification. Yeah.
So how do you deal with the data for this? Because the subset of problems that we have, they need a different set of data, right? For example, it's a classification, you need a label set of data. If it's question and answering, you just need a Wikipedia article, the data requirements for each of these tasks are different, right?
Yeah.
So if you have built one giant model, so how do you deal with the data problem?
Yeah, also a great question. So each one of these comes with a supervised training data set. They're kind of different sizes and different qualities, and again, Nitish will talk about a lot of that.
Okay.
But we do need data for each of these tasks. We're kind of assuming that this is the basis set that we use data for. Yeah.
How could you decide whether the data you have or quality of data you have is enough for your task?
Yeah, that's a great question. We don't. We have no idea, right? If you had more question answering data, you'd do better on question answering. If you had more semantic related data, you would do better. We basically tried to get the standard largest corpuses that were publicly available so that we could study the multitask learning problem in that context. But this isn't necessarily like if you really wanted to train a model for question answering in production or something like that, you would probably want to go get as much question answering data as you could and not necessarily just use this data. So this is really an experimental environment that we're setting up, and in most cases, yeah, more data is going to be better. Yeah.
I have a question of how do you shortlist the 10 tasks? Do they have some kind of intrinsic overlap? Because there is on multitask there is not one task benefiting from the other as well, or was this an approach towards generative?
Yeah, so we've talked about this kind of after the fact a lot, where when we were picking these 10 tasks, we were kind of intentionally picking tasks that we thought were very different. The one thing we know in multitask learning is that related tasks help each other. So if you take two question answering data sets, they're probably going to help each other. So for understanding the multitask problem that we're getting at, and again, we'll talk about more of this afterwards, we wanted a diverse set of tasks, something that forced us to design the model in a way that didn't focus on any particular one. So this is really a diverse set of tasks that kind of challenged us to make a general model. And in some sense that does make it harder. So yeah, if you had other kinds of question answering tasks or something like that, you probably see different effects than what we're seeing. Okay, so kind of on that note, what we do by framing everything as question answering, for each task, we don't ever tell it directly kind of like what task it is, right? And we're not designing the model to do sentiment analysis or to do translation. So we have to design the model in such a way that it can feasibly do all of these tasks and learn when it's doing which one. So in that sense, it has to be able to adjust internally. And what we've seen is that this then opens up a possibility where you didn't have it before, where you might be able to do some sort of zero-shot classification or zero-shot behavior, because now it's, I understand that I'm generating positive when the sentence is positive, and if you ask me if it's happy, I might also be able to tell you whether it's happy or sad. So because there aren't just two classes at that point, it can actually work in the space of language and maybe have some zero-shot effects. So building on that, this is really kind of coming from Colder and Weston, kind of back in 2008. They were our main inspiration for this. They had like this unified architecture for NLP, and they had a different set of tasks, things like NER and sequence tagging, chunking, things like that, where we have a different set of tasks. And there's been a lot of work on multilingual translation, or models that do speech and vision together. And the last one on here I want to mention too, because that's another multitask benchmark that is actively worked on right now. And it kind of frames everything as classification or regression problems. So it doesn't have tasks like machine translation, where you have to actually generate long sequences, but it's kind of it's a nice little crucible for doing similar multitask experiments. Okay, so I want to get into the model for just a little bit. High level, this just goes in line with everything I've been saying. So the model here, it's not totally essential you understand this, but the GIF, or the GIF, is just showing that for these different tasks down at the bottom, whether it's machine translation or summarization, everything just gets a context of question and has to generate an answer one word at a time. Whenever we talk about something called like a pointer switch, it's essentially choosing whether it wants to focus on the context, the question, or the answer. And I actually don't see the time, so what time is it? 82. Okay, so I'm going to switch to Nitish, and he's going to walk you through the model and some of the experiments. So especially during this part, ask questions if something doesn't make sense.
Sure.
If you care.
Yeah, so I'm going to go through the model, but I'm going to try and keep it quick because there's a lot of interesting stuff that I guess would be more relevant for the audience near the end. But the essential idea is that we built this model knowing that the tasks that we chose were kind of not helping each other. So if you had 10 classification tasks, you can exploit that. You can use the idiosyncrasies of those to build a network that sort of specializes for those 10. But since we have such a diverse set of tasks, we had to make something more general. And what I mean by that is machine translation, where you have to generate one word at a time from a vocabulary of like 800,000 words, is very different from squad-like question answering, where you know a priori that your answer is going to be in your context. So if it's a Wikipedia article about Tesla, I know that his birthday is going to be in the document. So I can use the fact that I don't even have to have a vocabulary. I don't need a dictionary. What I can do is just know the words that are present in my context and essentially roll over those until I find the one that matches. And that's what a lot of the state-of-the-art squad models do. They end up choosing from the context and they don't even deal with the generation. But we have to have both. Plus, we have to have the ability to do classification, where the way we set it up, we're constraining the answer space by asking the question. So we ask, is this sentiment positive or negative? So then the model has to learn that it has to point to those sort of tokens in the question, the positive and negative, because it's easier to do that than to go through the entire vocabulary of 800,000 words to find the right match. So just to boil it down, what he mentioned was this notion of the triplet, the question, context, and answer triplet. And what we do essentially is very similar to co-attention networks for question answering, if you've heard of those. You start with the question and the context, so that's what you start with. You have your n-gram embeddings, your fixed glove vectors and whatnot, the classical spiel. You start with an encoding that we composed of LSTMs, and that's only because it's one of the obvious choices to start with here. We add a layer of co-attention, and the idea for co-attention is essentially that if I ask you a question and I give you the paragraph, it's very likely that you're going to first read the question and then read the paragraph to figure out quickly where the context is going to be. So if I ask you, when was Nikola Tesla born, you're not going to be reading about his inventions or late in his life, what he did or whatnot. You basically boil down to the essentials of his early life to figure out if that's the place where you should focus on. And that's kind of what co-attention does. It sort of maps the two sequences together to see if there's alignment and uses that alignment to create a soft attention around the words that matter. So it makes the job very easy for the downstream layers to use this information. We then sort of have more encoding on top. We use transformer layers, which are these recent layers that have shown to be really good, have amazing performance for a lot of tasks, including language modeling and translation. And then we ended up with another LSTM layer just to finish off our final encoding. And just as a side note, a lot of people ask us, why did we make the choice of LSTMs? Why not go all transformers? We would love to do that, and we would love if someone succeeds at it. We just couldn't get it to work for some reason, but yeah, it's one thing that we're really hoping to get, only because we'd get amazing speeds. But for the moment, it's sort of a transformer layer sandwiched in between two LSTM layers. So that's the encoder side. That's what gives us the entire question and the context sort of boiled down to a couple of vectors. And then we have the decoder layer that starts with the answer, which during inference time would just be something like start of sequence token. It also has a similar sort of multi-head attention LSTM kind of structure. But then there's an interesting part here, which he was mentioning earlier, which is that there are 3 choices to come up with an answer. And this is where it's kind of like the modeling choice got really critical. Is you have to have the ability to generate from a vocabulary, and because that's the only way to do translation. You have to have the ability to point to the context, because that's the only way to do question answering. And you have to have the ability to point to the question, because that's the only way you could do classification. So to allow all of those 3, we essentially have 3 choices. And the model, again, everything is end-to-end trained, so the model is making all of these decisions. There's no point at which we are intercepting the model and saying, oh, this is question answering, you should be activating your context pointer. We don't do any of that. Essentially, the model does that on its own volition, and essentially it's basically a sigmoid that decides between 1 of 2 choices, and there's sort of a hierarchy of 2, where it first decides whether to point or to generate, and within the pointer it generates, it decides where to point, whether the context of the question. So once you compose all of that together, you get this final distribution. You put a log softmax on top. You put a cross entropy on top. You backprop all the way into your first layers, and essentially you go through the training process in that run. So that's kind of what the model is. I'm going to go through, unless you have more questions, I guess we could go directly into the evaluation mode, which where things get interesting. Is the choice of the question, sorry, you had a question.
Yeah. So would you simply go over each layer, try to explain like what each one does?
Sure. So the first layer essentially is the encoding. So that's where we take the numericalized word embeddings and then we encode them with glove and character anagram. We have the LSTM layer that essentially goes over the sequences, which are the way we set it up, and I guess I'm going to talk about it in more detail later. But the way we have set it up is each mini batch is 1 task. And we go across tasks via mini batches. So it's a mini batch of question answering, mini batch of translation, mini batch of sentiment, and we run through the 10 tasks and we cite it. So the first layer is essentially a packed LSTM where we go over the entire sequence. We have the co-attention where it's essentially the context and the question laid out, and they have bidirectional attention. So I guess it's kind of like saying you have the first step of the context, which highlights what's important in the question, and the question that highlights what's important in the context. The transformer layers are more interesting. They essentially are purely self-attentional. They have no recurrence in them. So what they essentially do is have a vector of, so your time sequence vector, so you have like t of those vectors of say 5 to a dimension. You essentially dot product them with themselves, and then you do a softmax. And what that essentially does is it enables any word from the context to speak with any word, and whichever interactions are more important get highlighted, which the next layer can then focus on. And then the LSTM does more mixing. So all of this really is about mixing, right? Because you initially start with everything as being a sequence of tokens, and then what you really want is interactions between tokens to get highlighted. And then really the decoder is just pretty much the same thing. It's just a copy of transformer LSTM transformer, where they have the exact same role. They're still doing sort of mixing in terms of on the decoder side, where again, if you're doing it on the inference side, you'll be sort of doing it 1 word at a time, but the goal is essentially the same.
Thank you. Are the question pointers and index pointers more like a classification thing where you say like you point to this particular index in the question, like this particular word?
Yeah.
Is that what you guys do?
Yeah, that's exactly what they do. So yeah. So going back to the tasks, so we have 10 tasks that we talked about. Each of them has this one data set that the community obsesses over, really. So squad for question answering, IWSLT for sort of low, if you have a low resource sort of pair, that's a good place to go. summarization, CNN Daily Mail is still really, really popular. And then there's the rest where essentially, again, there are more popular data sets where people benchmark on them all the time. The interesting thing is that each of them comes with their own fair metric. So if you're talking about squad, people aren't going to be interested in some form of accuracy. I mean, they might be interested in exact match, but very likely what they're going to be interested in is some NF1 score, like a normalized F1 score. If you're talking about classification, very likely people are going to be interested in exact match. They are not interested if you have, if you have a good recall, but you're not going to have a good accuracy. That's kind of not interesting if you're doing classification. Things get more interesting when you're doing wiki SQL, where you're trying to propose a well-formed SQL query. So it really depends on whether that's executable and it gets you the right answer. So it has a logical form exact match, which is the metric of interest. You're not only interested in making sure that the SQL queries match. So the idea is that essentially all of these metrics are community specific. So we're trying to make each community happy. But at the same time, we are sort of lucky in that all of these are scaled 0 to 1 or 0 to 100, the way you think of any way you think about it. So what we can do is essentially compose all of them by a sum and say that that's a decaScore. So it's kind of unfair. We agree that we say 1 point improvement in sentiment analysis, which probably takes half an hour of tuning, is the same as 1 point improvement on machine translation, which is 6 months of effort. But we'll come back to why we think this is a reasonable choice. But essentially, to avoid all sorts of reviewer controversy as well, we just say sum it all up. Like that's a fair way of gauging performance. If you improve all of them at the same time, you get a better score. If you improve one thing and don't hurt the others, that's fair too. So a sum is essentially what we go with. And what we started doing now is training all of them. So we have our McCann model, which was a 3-arm sort of model that we spoke about, and we started getting some interesting, results on those. So squad was like 70.8 and IWS was 16 and so on and so forth. But the idea is that we were able to train this model to reasonable performance on all of the data sets. And again, this is not state of the art on the individual ones, except 1 or 2 of them. But it's amazing that we were able to train quite a lot of them to accuracies which other models of the same nature could not get to. And some of them are something like seek to seek. So one of the most common baselines, if you have no idea how to design a model, if it's a completely new domain, is to go into like a completely vanilla sequence to sequence model, where you essentially take the input sequences, you have an attention, you start decoding one step at a time, no hacks, no pointers, no fancy sort of transformer or attentional layers, and you start seeing a significant gap in performance. So it's like a difference of like 513 to 562. And then you can sort of go back and fill those in. Like you can incrementally go and say, if I take a seek-to-seek model but I add co-attention, I get this. If I also add transformer layers, I get this. But by building it up to that performance, you start seeing that certain sort of trends are very consistent. So for instance, co-attention seems to help squad quite a lot. IWSLT significantly benefits from having more complexity in the network, and ZRE, which is our zero-shot relationship extraction, kind of tracks squad. So if squad improves, then ZRE improves as well. And that's kind of what he was alluding to earlier with the comment about tasks helping each other. And all of these, I want to emphasize, are completely multitask. So they are not individual models that sort of you take squad, you train squad, you take IWSLD, you train IWSLD. This is taking all the data sets, sort of smoothing them together and then pushing them through the model and then getting scores. What you can also do though is look at single task performance. So what you can do is take the same McCann model but train it individually on each task and see how well it does. And you start seeing there is a significant gap in performance. So for instance, just to highlight squad again, it's like 75 if you just train it by itself. If you train it with a lot of other stuff in it, it's 70.8. So you start seeing drops in performance as you start co-training. And this is somewhat expected because not everything will help each other. But this is kind of a bummer as well, because this is the kind of the problem that we were set out to solve. And you can fill in the whole thing, And you can start seeing these trends, and there's some interesting analysis in the paper. But the core idea is that the gap is not going to be terminated just through model choices. So if you try to say that I'm going to take seek-to-seek models, or I'm going to take co-attention models, and then suddenly the gap is going to disappear, that's certainly not going to be true. So one of the things that you might want to know is then, where does that gap come from? And one thing that we thought was the problem was that the model doesn't know what it's doing. Like if I give you a pair that says, Bryan went to school, and then translate this to German, we weren't quite sure if it didn't know that it was doing translation, or it wasn't just good at translation. So what we did was to try to probe the model to see, does it know what it's doing? And the way we did that is essentially to look at what tendencies do the pointers have once you start doing inference. So what we expect is that things like IWSLT, which is translation, are completely focusing on generation. Whereas squad, which is basically point to the context, have a completely context pointer. And we start seeing that this is not a problem. It's not confused about what it's doing, it's just bad at what it's doing. So this was good, because then what we could focus on is training strategies. Because if it's not a modeling issue, if it's not a sort of confusion of what I'm doing issue, then it's necessarily a problem of training. And that's when we started looking at a lot of heuristics for how we could improve the training. And we had like 3 sort of meta directions that we wanted to explore. The first one is fully joined. And that's sort of my comment that I was making earlier, where it's really hard as an engineering problem to mix batches together. Because if you have summarization, then you have like a really large sequence. If you put in a 10-worded sentiment, then it's kind of, you're wasting a lot of effort in padding. Also, it's like really hard to batch things and oversample them. So just in general, we thought that it's a much simpler choice to just go and say, each batch is one sort of unique task. And what you can do essentially by that choice is just cycle through the tasks. So you have batch task A, that gets the batch first, then the second, then third, and the fourth, and the fifth, and sort of you cycle. So you go back and through again. And we got reasonable performance with it, right? So you start seeing reasonable decaScores. But one of the things that we thought was going to be interesting is the concept of transfer learning within the model. So what we are really interested in is what the performance of the model is at the end. We aren't quite interested in how we get there, right? Because that's kind of like a byproduct of the choices we make. And one of the things that we wanted to explore was curriculum training. And by that I mean, let's start with the more interesting tasks. Let's start with the more difficult tasks. Let's prioritize them. Let's sort of warm the model with those tasks. And then let's put the rest in. Or you could go the other way around. But one of the things that we found necessarily helped was just sorting the tasks based on some notion of difficulty and then cycling through them first before putting all the others. And if you have, like, for instance, squad and IWSLT and summarization, which we thought were very rich because of the size of their data and just the complexity of the problem that you're trying to solve, we found that that was quite useful in pre-training the model before you start the rest. So if you have task A and B, which are sort of more difficult, you could start sort of cycling through them and then add the rest in. And then I could go into more at the end, but the third heuristic is this notion of oversampling, where we realize that certain tasks are not represented sufficiently because of the way that the model mechanics interacts with the task. By that I mean, IWSLT is pretty much the only task, like machine translation is the only task that uses the vocabulary, that generates over the words, all the possible words. So if it's the only task that uses the vocabulary, you're going to see that by the time that it comes back around in its cycle, it sort of lost that. It goes through this process of catastrophic forgetting, where all the other tasks have overwritten on what it thinks is important, and it's too late. So you improve your blue score in the meta batch, but then you lose it all once everyone starts overwriting over you. So the way we thought about it was to have IWSLT, or like machine translation, twice in the loop. And that's almost like saying we double the data set with some cadence of the training order. But the idea is essentially that we want to make sure that the mechanics of the model, the way we structure the pointers, is in line with what we expect from the dynamics of the training loop as well. And the idea, again, like just to go through the same cartoon image, is the A, B, C, D, and then you go back to A, which is in our case machine translation, before continuing on to D&E. So this is where things get interesting. So we started off with McCann being at 563 and the bag of single words being at 586. So it's almost an upper bound for performance, but not really, because if things start helping each other, then you can start exceeding it. But this is where we started off from. This was a fully joined, sort of cycle through batches, no choices to make, and bag of single words, same model trained on different, on all the individual tasks. So the gap started at about 23. And this is what annoyed us, this is what we focused a lot of our effort on. When we added in the pre-training, where we said, let's take the important task. In our case, we took squad, because it's like, if everything is question answering, let's start with the question answering first. So for 75,000 iterations, let's start by only training squad, and let's throw the rest in later. We got up to 571, which closed the gap to about 50. That's kind of nice. We are down to a gap which could reasonably could be filled with tuning, but then we did what was seemingly a good decision. We added in COVE, which is contextualized word vectors, which we talked about, which uses sort of, which is a form of transfer learning where we trained a lot of machine translation and then stuck it as an encoder for the first layer. So along with GLOVE, you use this COVE or ELMO, which is another such contextualized word embedding. And we start seeing that it lifts the performance overall. So everything went up quite a bit, but the gap increased from 15 to 25. So it's sort of back where we started, which was a bummer. But then that's when we started exploring, that's when we had the sort of epiphany that it's not about the training, it's not about the model, sorry, it's not about the model, it's not about not knowing what we are doing, it's about training. So we started putting in more emphasis on the training strategies. So by putting in back anti-curriculum, we get a 609. So the gap is around 9 points or 5 points. We started putting in oversampling, and that's when it got to 617. So that's about a gap of 1. So this is like fresh, pretty much from the oven. This is the results as of last week. So we pretty much are able to meet within some epsilon errors and whatnot, the performance that you get from a bag of single words model. And I want to emphasize something here, that on an individual task, we might not be state of the art, and it might be sort of the problem that you still lose performance and gain performance in the multitasking case, but overall, if you aggregate it based on the decaScore, then you're almost the same. So if the metric that you're interested in is the sum of all the individual scores, you're no better off by having 10 models than you are with having 1 model. So in that sense, it's a great step forward. But in the sense that we still are far away from single task performance on each of them, it's sort of a lot of work to do still. And I guess that's where I'll close as well. Is there's a lot of sort of open problems in this domain. So we sort of briefly touched on multitask learning and transfer learning and sort of pre-training and fine-tuning, but there's so much more that you can do with this. There's still a gap that exists between state-of-the-art performances for the individual tasks and the performance that we get. And there's also notions of zero-shot learning that we started exploring with, but it's still a lot of possibilities that we didn't. So as he mentioned, if you train on giving a movie review and asking, was this positive or negative, you can replace that by saying, was this movie review excited or unhappy? And it gets it, because it has not learned to do classification, it's learned to point. So because it knows the notion of the negativity associated with the word unhappy, it gets that. It knows that exciting is something that has a positive connotation, so it gets that too. So there's some sort of preliminary results that we have in that direction, but there's still a lot to be done there. And the same goes with domain adaptation, where I guess to your question earlier, where you could use decaNLP as a pre-trained model for doing something new. So if you were doing English to Czech translation or English to Swedish translation, instead of starting from a completely unwarmed model, you could start with this, and then conceptually it helps you, and we have some results that shows that it does. But it's sort of, again, there's a lot that can be done in terms of how you can do that efficiently and how you can enable that through the training process a priori, if you know that that's what you're interested in. But I think I'll close with that. These are some of the resources that we have. We have a website, decaNLP.com, where you can get access to our blog, access to sort of the papers, some of the decisions that we made. everything that we have written is, like in terms of code, even the pre-trained models are available online. If there is something that isn't there but you want, feel free to email us. We'll definitely be able to give you that. And if you have any questions, and we can't chat right now, please feel free to email